I'm Amanda Karakas. I'm going to be your lecturer for the first 4 weeks of this course, ASP3012. So I'm mostly teaching the stars component of ASP3012, which is stars and galaxies. Your course coordinator and lecturer for the rest looms down here. He can introduce himself.
I know most of you anyway from the first year, John Latenzio. And I'll be doing the last 2 weeks of the stars because Amanda's going to be at conferences.
I'm going to conferences. That's right.
And then I'll do the galaxies part as well.
Yes.
And one of us will be there for the observing night, depending on what night it is.
I'll go through that this first lecture is more of an introduction to the unit. So I'll cover the assessments and what we will be doing each week in the labs and the tutorials. And it's really just, I think, for us to get to know each other a bit. I don't know how much course content I'll go over. It depends on how much time we have. So yeah, this is really just an introduction. Do you have anything more that you want to? No? All right. Okay.
I'll hang around for a few minutes and I'll go and do something.
Okay. So they're us here. So before I get going, before I get to the introduction about this, we were asked to advertise the Science Industry Night. This is for mathematics, physics and astronomy students, and that's 6 to 8:30 p.m. Wednesday, the 7th of August. So if you're interested, please go along. This has probably been advertised through Moodle as well, so if you haven't received information about it, you can check Moodle. Anyway, if you're interested in the Science Industry Night, please go. Lecture S3 on the 7th of August. And we were also asked to advertise English Connect, which is conversational and academic English for people who either don't come from English-speaking backgrounds or just want to improve their academic English, which academic writing is quite different to normal spoken English. So it's one thing that as you move higher up through academia, you have to learn to write in an academic style, which is really different. So if you are interested in this, I notice it's been cut off, but you hopefully can see it. It's monash.edu/English-Connect. So if you're interested, anyway. Okay, now, we are going to ask you some questions during the course of this. We're going to try to make it a little bit interactive. We know it's hard in a lecture setting to make that interactive. We will try. It's not going to be interactive as ASP1010. For those I know, I can see some faces who've done ASP1010. But we will try a little bit. So what we're going to do is that I'm going to pass these around. Take one of these, fold it into a square, and we will ask you questions. Some will, at least in the beginning, will be super trivial, and then others will be harder. We'll get you to think about them a bit. So we have so of course for each unit we have to tell you about the assessment. It is listed on Moodle and on the unit guide, but let me just go over what that assessment is for this unit. You'll have 2 assignments that are worth 10% each. I'll run through, I don't recall now if we list when the assignments are here, but we might include them. We have decided when they are, but
We have, I'm not sure that they're in the unit guide.
I
think they are.
Okay.
We can sort of tell because in the labs it says which lab is set aside to do a new assignment.
And I will get to that. So I will look at the breakdown of the labs soon, so that will give us an indication when the assignments are. There's also one observing night that's also worth 10%. And I'll discuss a bit more about the observing night next. There's also lab reports that total 10%. So the labs, except for this week, are assessed. So this week is really an introduction to Linux and computing. For those of you who don't have that background, that is the so Linux is the operating system of choice for most of us, and computing. Most of us have to do some sort of computing when we do stellar astrophysics, and so I actually don't mind what sort of background you have in terms of computing. I don't really care that much as long as you can do some, but there are others in our school who have stronger views than me about that. Okay, then you have a final exam totaling 60%. So this is how we're going to break down the assessments. Now, first I'll discuss the observing report or the observing night. You'll have one evening, so this is just a once-off evening of observing, as that'll be about 3 hours. Yep. It will obviously depend on weather, so we have a few nights set aside for this, but this will be roughly in week 9. Okay. So this will be on campus. It'll be in that green, it'll be in the lawn area in front of the big screen near the student centre. So that's where we'll hold it. And you will write a report on the objects that you observe, whether that be stars or globular clusters or something related to content related to this course. Now this is the first time I've taught this particular unit, so I don't know what goes on in the observing night. Apparently I might be there this year, so I'm going to be helping you guys. But John knows more about it, so do you want to say a few words?
No.
No, right.
Well, I think the man just covered it. We'll there'll be half a dozen the Dobsonian telescopes set up, and then one telescope will be connected to the big screen so that it can actually integrate over time, and so we can show fainter objects there. And then you'll go around and look at various things through the telescopes, and then you'll be so excited by one of them that you'll just be drawn to have to write a report about it. And so that's what you'll be marked on. And then you should point out why that object is relevant to this unit and what's known about it.
Well, they have to write a report on something regardless of their excitement levels, I think, John.
Well, that's true.
So, yes.
I'm just confident that the excitement level will be almost intolerable.
Really? Right, well, but the idea is that with the observing, astronomy is an observational science. It's not just, so while much of the content in this unit is theoretical, so we really are looking, so my content, I'm looking at stars and stellar astrophysics, is really from a very theoretical perspective for the most part, but astronomy is an observational science. We learn everything about the night sky, or a lot of what we learned about the stars and the night sky comes from observations of it. So we thought that it's important to have some observational component in this unit. We used to have a stronger one, but I think we have managed. This is the best thing we can do right now. And it really is. So the idea is to flesh out some of the ideas that you've covered, some of the theoretical ideas you've covered in this unit. Okay. So apparently that's what happened last year.
Maybe the year before.
All right, there you go.
Yeah, we actually got a cluster of galaxies, which I was pretty surprised by.
Really?
When they said they'd
Which
look at a
cluster
cluster. I said, there's no way you'll be able to see a cluster of galaxies from the middle of Clayton with all the lights, but they did.
Mm. Hopefully it'll be warmer by early September too. All right. Okay, so how are we going to structure the unit? It's actually sort of broken down into two halves. We have the first half of the unit, first 6 weeks is on stars and stellar astrophysics, and the second half is on galaxies, broadly. Now I would normally cover all of the stars unit, all the 6 weeks, but this week, as John mentioned, I'm going to conferences in Europe, so I'm going to be away from week 5. But I will still be in contact. I'm still going for work, so if you have questions about the content of the unit, you can still contact me, and I will give you dates about that. Now, the galaxies is the second half, and that's be mostly covered by Lattanzio, but actually, when he says mostly, I'm not sure. I can be at some of the tutorials, but I'm not sure.
No, I'll be doing it all.
Right, he will do the galaxies. Of course, there's overlap, of course, because stars are the main observational component of galaxies. So understanding stars is really the first step to understanding galaxy evolution as well. Okay, and we've tried to give an example of a beautiful star cluster and the Hubble Deep Field. I notice it's actually cutting off the bottom, so I'm going to have to worry about that for future. Okay. Now we have a few references. Some of them are so probably the main reference that I've used, at least for the first couple of lectures, is Carolyn Ostley. Some of you may have a copy of this book. If you don't go and buy it because it's expensive and it's really is more of a doorstopper but there is, of course, you can access this book through the Monash Library using your Monash account. So I recommend if you don't have a copy, go through the Monash Library. There's the best way of getting it. We have used in the past some of these books. Don't buy them again. There's probably library copies of them. These might be hard copies though, old-fashioned. And then I have been using recently, there's an ebook online which you can access again through your Monash account. That's called Understanding Stellar Evolution, and it's published only a couple of years ago, and I really like that. It's quite short in the content it covers, but I think it nicely covers much of the material we do, and in fact even more so. They have many chapters on binary star evolution and other things that we just don't have time to get to with this course. So that's also, I think, I definitely recommend that as if you want to have a free book that you can also download a PDF of this, again, through your Monash account. In terms of galaxies, we have a few books listed. I think, again, the main reference is this book, is that right? Maybe you can mention what your main reference is.
Probably the one on the right. The one on the left and the one on the right. Carolyn Ostley is okay. It's not so good for the stars part. It's a bit light on in the stellar structure. There's nothing on polytropes.
That's probably not.
Which is not bad either. Anyway, the book on the right by Linda Spark and J. Gallagher is available free in PDF form on the web, so you can download that, and that's actually a pretty good book, I think. And the other two, Binyam Tremaine and Binyam Mahalis, are a bit advanced, but if you want something, it'll almost certainly be in one of those books.
And again, they should be in the library.
Yeah.
There are probably library copies of those books. Okay, so they're the main references that we can draw from. Of course, you can use our, I'm not sure what's going on there. Of course, our notes are also should be a reference for you. So depending on the sorts of material we're going to cover, so for lectures 1 and 2, I'm going to post the notes as a PDF after my lectures. But for the more mathematical lectures, I'll post the notes beforehand. So you can download the PDF copy and print it, or you can make notes on the PDF copy, whichever works well for you. That's especially for the more mathematical ones, because I know that sometimes following what I do might be a bit difficult, and it helps for you to take notes. Also for the more mathematical notes, I will be turning on lights and I will be doing stuff on the board as well. So sometimes it's more helpful if I just run through things slowly on the board than it is if I just give you the derivations in PowerPoint, because I find that it's very easy to flick through things really quickly in PowerPoint, and you may not have time to absorb it. So I will run through some of the more complex stuff by hand, which I think will be slower, and it'll give you guys time to hopefully absorb it. Now, in terms of the weekly classes, so there are weekly 2-hour labs. These are marked, and I mentioned contribute 10% of your final mark. There is a pre-lab exercise, and that's included in the final lab mark. This is to get you guys thinking about what the content of the labs beforehand. We, as I mentioned, use the Linux operating system, if possible. Many people use Fortran, at least for really computational stuff, but honestly, most day-to-day stuff is done in Python, I think, in the astrophysics community these days. In terms of the lab work, you submit work on Moodle the Monday after.
Except we changed that.
Is it?
Yes, we changed that because the labs at the start of the week, after we prepared that, the timetable changed. Okay. So now you submit on Moodle by 5 p.m. on the Friday, and then you should get it back before the lab, which is Monday and Tuesday.
Submit work on Moodle when? Sorry.
Friday, 5 p.m.
Friday, 5 p.m. Okay.
So we put a second lab session on. So there's 2, Mondays and Tuesdays, 9 to 11. So you should try and arrange yourselves so that you're roughly equally distributed if you can do that. Because fewer people in a class, the more time you get with the tutor anyway. So try and do that. I mean, the first week's obviously going to be a bit of a mess because we only got the second time on Friday. So, but yep, try and do that.
All right.
And the last week of semester is just like all the others now.
Hand in on Friday.
Hand in on Friday.
Yeah, exactly. That's right. Okay, so we have a lab schedule. So these are for the computer labs. So week 1, so we've broken it up. That the first 6 weeks are stars labs, and then the rest of it are going to be galaxies labs. Of course, we have a break around the end of September. So this week, of course, is just an introduction. It's not marked. But then after that, we're going to be looking at ordinary differential equations, really? Anyway, polytropes, hydrogen burning. This is clearly when assignment you're going to be working on assignment 1, because this lab will be dedicated to assignment 1 support. Then there's going to be something about the sun, and that is not a galaxies lab.
No, but you have to have the material first. The labs, there are 4 labs for each half, and they're a little bit offset because the intro and the ODEs are sort of relevant to both.
Okay.
So then there's 4 labs on stars and 4 labs on galaxies.
Right. Anyway, I think we should change this anyway. And then so you're going to have some galaxies labs, and then you have assignment 2 support down here.
Yeah.
Toward the end of the semester.
Well, the topic is the lecture topic, not the lab topic.
Ah, right.
But okay.
Yeah. Right.
We could just delete that column.
We could just delete that column, yes. All right. So we also have a tutorial schedule. So we have tutorials, we have 1-hour tutorials. These are not assessed, but these are to help you. These are important because we cover exam style questions in the tutorial. So these may not seem relevant right now, but they will become relevant as you are approaching your assignments and as you're approaching the end of semester when you have to prepare for your exam. Now, I know I've gone through my own undergraduate experience, and I know it's very easy to leave it all to the end, to the last couple of weeks when you do your exam preparation. But my recommendation is, if you are serious about this unit and you really want to get very good marks, that you want to start at the beginning with the tutorials and start working through the material, because that will give you, that'll mean that you have the preparation, you aren't cramming at the end. So that's my own advice there. However, it's up to you and your own timescales and how you work. So we will, in terms of the tutorials, we have topics again, we've broken them up, so we have 6 on stars and 6 on galaxies. There really is 6 in this case. And we will have, so the first week is just, so we have our first tutorial even today, and that's going to be at 1 o'clock, and that'll be in this room. Is that, where are the tutorials?
I think it's in here.
Yeah, in here. And then, so the idea is that we will be at the, so there'll be a TA at the tutorial, and we will also be at the tutorials to help. So this gives you an extra opportunity to consult us if you have questions, if you come along to tutorials. I might not obviously be making all the galaxies ones because I'm going to be away for a few weeks, and John might not make all the stars ones, but we will try and endeavour to be at as many of them as we can to answer your questions. Okay? And there will also be specific questions that we'll work through during the tutorials, and then there'll be extra stuff that you can take home and work on as well. That's how.
Yeah, there's 2 sheets. There's a tutorial sheet, which is problems that will get preference in the tutorial, and then there's an exercise sheet, which is more stuff that you should do in your own time. They may rely on stuff that you've done in the tutorial. The idea is that we help you with either the more complex or the more fundamental stuff in the tutorial, and then you can do the others. You shouldn't think that the tutorial sheets are the important ones and the others are not. That's not true. Tutorial sheets are just here to make sure you've got assistance with those questions, and they'll be specifically done. You're free to ask questions about any sheet at any time, of course, and you really should be doing both sheets.
Look, or even questions about from the lectures. If you have specific questions about the lectures that you didn't feel comfortable asking one of us during the lectures, you can come along to the tutorial and also ask questions if you don't understand something in particular. And in terms of feedback, so feedback both from you to us and likewise for us to you is really important in terms of your understanding as you work through the material and you learn about the content. So we encourage you to use the Moodle discussion forum. And this is, so even if you have a particular question, I think it's better to go, especially if it's something to do with the stellar physics or a question about the maths or something, use the discussion forum, because that way everyone benefits. So while you could email us directly, if you put it through the discussion forum, I think it's a better way, because then everyone in the class can benefit from, if you aren't clear about something, there's a good chance someone else isn't clear about something too. So we encourage you to use those. There are, of course, other ways to get feedback. I already mentioned the tutorials, and we also have consultation sessions outside of the scheduled classes, and I'll get to those next. Now, we are, of course, here to help you. We are really, I mean, both of us are really interested in this subject material, stars and galaxies. This is something that we both do research in. So, but we need you to come to us if you have questions. If you aren't clear about something, if you're struggling with some component, some concept, or some particular mathematics, we aren't mind readers, so you have to let us know, and so you have to provide feedback about that. Now, how you do it's up to you, but it's important that if you're struggling, don't just sit quietly, come and find us, or come and post something and just let us know what's causing you some concerns. Okay. Anything else to add? No?
Well, you just assumed we knew the answer. That was the only difficult part.
Well, we can.
We'll find out.
We can find out. So. Okay, so we are also available during the following hours. So I've set my consultation hour to be Thursday 3 to 4 p.m. before the 4 p.m. lecture on Thursday. So that's when I'm available in my office. So my room is room 133 on the floor down below, toward the end of the corridor. John's office is next to me, room 131, and he's going to be available Thursdays 2 to 3 o'clock. So if you have particular questions and you think you need one of us to sort it out for you, you want to come and see us personally, we will be available then. Obviously when I'm away, not in Australia, I'm obviously not going to be available then, but I can still be reached by email or by the Moodle discussion forum during those times. So I'm away from the 24th of August till the 17th of September. Actually, the 17th I'm in Sydney, but that's still, anyway, that's really, I'm still not at Monash. You're around all semester? You don't have any travel plans to mention?
Just the odd day. I think mostly I'm here on Fridays, which is okay.
Okay. So, well, we can be reached via email, but as I said, especially questions about conceptual stuff or you don't understand something that we've gone through, it's best to go through the discussion forums because then I think it'll benefit everyone. Okay. We also have an approximate lecture schedule, and this is where that topic, stars and galaxies, I think originally came from. So we have broken it down, as said, the first 6 weeks roughly on stars, the next is on galaxies. So this today is really an introduction. Then tomorrow, well, it depends on where I get to today, but then we're going to be looking at timescales on Wednesday. So timescales of stellar astrophysics, which are really important if we want to understand how stars evolve and change with time. And then Thursday, we're going to be looking at compositions of stars, and we're going to start thinking about basic thermodynamics, such as equation of state, and also other concepts relating to that relate to composition, like mean molecular weight. Then we have thermodynamics, simple stellar models, etc. And then I will take you through to the end of week 4, and then John will take over for what I was probably almost say the more fun stuff. The lucky guy.
No, the fun stuff and massive stuff.
Well, we can also get neutron capture and chemical evolution.
Yeah, neutron capture.
Yeah, that's good. So, anyway, okay.
It's all good.
Yeah, so I guess the stuff I'm going to take you through, so especially the thermodynamic composition of stars, the stellar structure equation, these are the basic building blocks, if you like, that you need in order to understand how stars work. So, okay, so what we will cover in the stars lectures. We were going to look at the interior structures of stars, and in particular, we're going to ask the question, what keeps them stable over time? So we were going to start with our sun, which is our closest star, and we will look at our sun and look at the timescales of our sun, and we're going to think about its energy and how big it is and those sorts of things. We're going to look at how stars generate energy and how they shine, how stars evolve over their lives. And evolve is a funny concept. We use it in a different way to biologists, because evolve is something, of course, it's from generation to generation to generation. It takes billions of years. Stellar evolution also takes billions of years, but now we're talking about one object, really. So it's really how stars age. Maybe aging might be a better word to use in some sense.
I actually had this argument with someone once.
Yeah, you know, maybe.
And I told him he was using evolve the wrong way, and he said, no, the biologists have attached their definition to it. We don't have to go along with theirs. The original definition was slow change, and he said it's exactly what we're talking about.
Well, I'm not going to go into. I don't want to get into that argument about it, but in the current, I guess, how most people learn the word, it is different. So stars, of course, can live for millions or billions of years, depending on their mass, and so this is an important concept that you'll also learn about. We'll also look at how they die, because how a star dies depends crucially on the mass it was born with. So we will look at that breakdown. Okay, we're also interested, so stars also play an important role in the universe. Stars make the elements that make up us, except for hydrogen. So we want to look at the processes that occur inside stars that make those elements. And that's actually something that I work on in my research a lot. He does too. Nuclear, so this is that concept of nucleosynthesis, the synthesis of elements. And this relates to then, this feeds into the chemical evolution of the galaxy. Because of course, when the universe formed, we think that there was only hydrogen and helium. Might have been some trace lithium, but it was so little of it that we can basically ignore it. Just hydrogen and helium. So all the other metals, if you like, again, I'm being lazy and an astronomer, came from stars. And so we want to look at those processes. And once stars make it, they put it into the interstellar medium that gets churned and mixed, and out of which you make new stars. And then you have this process of galactic chemical evolution, which takes place slowly over time in galaxies. So we will also look at this as well. Galaxies these are the topics we're going to cover there. And when I say we, I'm using the royal we and saying John. So John, I don't know if you want to speak about these? Or you can read that if you like.
Dynamical motions, distances, spirals and ellipticals. Anything that's not a spiral or an elliptical is called an irregular.
Does need to be the case.
Yeah, interacting galaxies. Incidentally, in the labs, you'll actually write a code that will enable you to collide galaxies together. So it's actually good fun. I don't take any credit for that. It was written by Daniel Price, but it's really, really good lab. You start off putting an orbit, something in a Keplerian orbit in the first week, and then by week 4 you're colliding galaxies. It's
pretty cool.
Good. That's all straightforward, I think.
Oddly enough, the Large Major Link Cloud's actually a spiral, not an irregular. It's off topic, but well, it's on topic.
No, it's on topic. It's not a grand spiral.
No, it's a
scungy little
it's a tidally distorted spiral. Okay. All right. So we want to understand stars and galaxies quantitatively. So it's very easy to look at pretty pictures, but astronomy is a very visual science, but it is not just about pretty pictures. It is at its heart a quantitative science, and we want to do things properly. We want to look at the stellar physics. We want to look at the physics of stars and the physics of galaxies. So this is what we mean by quantitatively. So we do use back of the envelope calculations, and by that I mean really simplistic order of magnitude calculations to get an estimate of things. And we will take you through some of these in the lectures, what we mean by this, really simple calculations, where we often would drop a factor of 2 because we don't, who cares about a factor of 2? We just want the order of magnitude. We will really concentrate here on the dominant features. But we also, if we want to do astrophysics really quantitatively, we need computers. And this is whether we're dealing with observational astrophysics or observational astronomy, or whether we're dealing with theoretical astrophysics, which is what we do in our research. So you need computers to do this, and use computer programs to either sort through your data if you have observational data, and there are really clever techniques now for doing this, or you write computer programs to make a model of a star or a model of a galaxy. And so these are, so really a lot of the modern, insight has come from the use of computers. So, and they are really, and that's often because, as we'll show you when we come to the stellar structure equations, we can make simple models, simple analytical models of this with the stellar structural equations, but really these are nonlinear partial differential equations that you can't solve analytically. So you have to turn to computers and solve things numerically. It's also useful for the interpretation of observational data. We're in the era of what we call big data in astronomy, where we don't have an observation. Let's say we go off and observe a star. We don't have one star now. We're dealing with, for example, from the Gaia satellite, billions information from billions of stars. So we have to mine that data using clever techniques in order to be able to find information from this. So we're in this. So you guys are actually in I think one of the most exciting eras in astronomy. You're students and you're coming into this era where we have, for example, information from the Gaia satellite, which is billions of. So we now have a good map of, for example, the distances to billions of stars in our galaxy. This is a significant fraction of the total number of stars in our galaxy, which is, I think, amazing. So really a different era of astronomy.
It used to be if you had data for half a dozen or 10 stars.
That's right.
You try and do statistics with that. Now, if you've only got 1,000, you say, oh, it's only 1,000, but it's okay.
It'll do.
Yeah.
That's right.
It's amazing.
Okay, so the night sky is, of course, full of stars. When we look out, if you're lucky enough to go out into a really dark place like Uluru, where this photo was taken, you can't see well here. But if you go to a dark spot, another really nice, if you go, for example, into the Victorian Highlands, or you go to Mount Kosciuszko, somewhere like that, away from the cities, you're lucky enough to look up and you see, for example, we're lucky also in the southern hemisphere, we have the centre of the Milky Way galaxy overhead, especially on a cold winter's night. So there are plenty of stars up there, but again, astronomy is a beautiful visual science. We want to understand how they are ordered, because they are clearly not evenly distributed across the sky, as clearly shown by this diagram. They are also not, there's also different types of stars as well. So we want to understand the physics of that and that ordering process. So both the physical ordering process, I think it's not a shock to say that this is clearly our Milky Way galaxy, but we're seeing it embedded within it. So we're seeing it from an interesting perspective. But then when it comes to so this is the structure that we see, but then what about the distribution of stars and the types of stars? So now we then have to think about their distances. That plays a part in how bright they appear to us. And we have to then, once we have them all on a common distance scale, which is what we use this concept of absolute magnitude, which I don't think I cover absolute magnitude, do I? They've already heard all about it.
Yes.
Okay.
At some stage, it might be in my lectures, we discuss
Maybe,
the effect of extinction on magnitude.
Okay. So this concept of how bright a star intrinsically is, that's really what we mean by absolute magnitude. And so once we have them all on this, once we have their intrinsic brightness, we want to then say, okay, then we want to look at their ordering, for example, on a common plane. And that might be, we look at their surface temperatures versus their intrinsic brightnesses. And then we can say, okay, what sort of, and we note then that stars aren't isotropically over this. They aren't distributed in an isotropic sense. We see clear patterns in this distribution. And we want to try and understand that. Okay, so maybe for the last 15 minutes or so, I'll run through, we're going to just talk about our sun because it is our closest star. And if we can understand our sun in a quantitative sense, again, quantitative, then we can get a good feeling for how maybe other stars work. And that assumes, although there's a number of key assumptions even in that statement, it assumes our sun is a normal star and it's going to be like all the other stars. So we want to come back and question this assumption as well. Okay, so our sun, this is our sun viewed from the SOHO Observatory, which is a space satellite at the, I think, L1 Lagrangian point, which is a place where there's I think it's equal gravitational force between the Earth and the sun. So this is a place where it's quite stable to put space satellites. And this SOHO satellite is pointed at the sun in particular, and it's observing the sun on a daily basis. And it observes the sun through all sorts of filters. And in these particular filters, we see the sun in UV filters. So we're seeing the sun in the ultraviolet in particular. So you can see that the sun, we see quite an active atmosphere in the sun. And I'll come back to structure in a minute when we look at the structure of stars. But we can see a lot going on. So let's try and think about this star that we know the best. Earth-Sun distance is something we know. This is defined at the astronomical unit. So here's a question for you. If the sun disappeared, we would see it, what? If the sun disappeared, we would see it disappear. Right, I did not write that. I have to fix that. Okay. Okay. So I told you that the first couple would be trivial. They will get harder. Okay. Okay. Yes, that. Okay, good. And we can look at that quantitatively. So we know what the Earth-Sun distance is. Here I'm sticking to SI units. You'll see that I will flip between SI units and what I'm going to call CGS units, centimetres, grams, seconds. And I'll get to that later. But we can do a really simple calculation. Then 1 AU is, so we have 1 AU here divided by the speed of light in metres per second is 500 light seconds, which is 8.33 minutes. Easy calculation to do. Okay, so let's look at the size of the sun. It's a big object. It's roughly 7 times 10 to the 10 centimetres. I actually think in centimetres, not metres. But we wanted to put it into metres. It's about 7 times 10 to the 8 metres. So it's at 700 billion metres. So the sun is big in terms of its radius. It has, if we want to compare it to the Earth, we can see that it's roughly 110 Earth radii. So that's how big our sun is. We can look at the comparison between the volume of the sun compared to the volume of the Earth, and that would just be this cubed. Remember, if we're looking at the if we look at the volume of a sphere, which is 4 over 3 pi r cubed, then we see that it's roughly 1 million times Earth's volume. So the sun is big physically, both in terms of its mass and also in terms of its radius. I'll get to the mass next. The sun is roughly 2 times 10 to the 30 kilograms, or how I think about it in my head, 2 times 10 to the 33 grams. So the sun's big. Now compare that again to the Earth, which is again something, it's the planet that we're living on. The Earth is 6 times 10 to the 24 kilograms. So the sun is roughly 300,000 times more massive than the Earth. So the sun is both massive compared to the Earth, and it's also big compared to the Earth in its extent in volume. If we compare it to Jupiter though, it's about 1,000 Jupiters. So Jupiter's the biggest planet in our solar system. And I tried to find this. There is a quote I read from somewhere, and I can't remember where this came from, and Google did not help me with this. But I heard someone once say that our solar system is really just the sun, Jupiter, and some rubble. And we are that, essentially. Because we are, in terms of both the mass and the size, we would be very hard to see outside of our own solar system. Jupiter would be Jupiter and then maybe Saturn, because Saturn's big in size, even if it's not as big in mass. Okay, so this gives us some of the intrinsic qualities of our sun, but what about the structure? Due to stellar evolution or changes over the course of a star's life, stars become highly structured. So this shows a structure. I just took this from Wikipedia, but this is actually one of the better figures I found because all features have been drawn to scale. So our sun and most stars have a similar sort of internal breakdown. we see a central core region, which is often where nuclear fusion reactions are occurring or have occurred, depending on the type of star we're thinking about. They also will often have, sometimes, but our sun doesn't have this yet, they will often have a shell region. And in this shell region, this is also, we can think of this in the central regions of the star. And in these shell regions, this is another place where nuclear fusion reactions are occurring or have occurred. Again, depending on what sort of star we're looking at. Then stars will often have an envelope, and that envelope is it's where we have a steep density gradient and pressure gradient. So you're going from a region where you have nuclear fusion and it's more dense, and as you move through the envelope, you often have this sharp decline in density out to the surface layers. So we have an envelope, and also they're not just structured physically, they're also structured chemically. Again, in our sun, the core region is where nuclear fusion reactions are occurring. So we're converting hydrogen into helium in the core. Where we think in this envelope region is fairly homogeneous in composition, and it's probably similar composition to what the sun was born with, but not exactly so. Stars then will often have an atmospheric layer, and this atmospheric layer usually doesn't contain much mass, but that's where the light escapes from. So we define a photosphere, which is where the majority, let's say our sun emits most of its light in the visual wavelength. So the photosphere is where the optical depth is less, it becomes less than 1 for most of that wavelength. That's what the definition of photosphere is. So for our sun, the photosphere is where the wavelength around 600-ish nanometers escapes, and that's located in the atmospheric region. The sun's atmosphere, and this is more something for such stars like our sun, what we will learn soon, our main sequence stars, that they also have this dynamic atmosphere, this chromosphere, and we often don't see chromospheres around other stars. So chromospheres are something that it's not especially dynamically active chromospheres. We don't see them around all types of stars. We do see it around our sun. Our sun's actually not very active, and we should probably be lucky because of that. If we had a sun that was much more dynamically active, I think we'd be in a bit of trouble. Okay. So density. Now I mentioned that there's a stratification both in chemical and physical structure. So let's think about the density. One way which we can quantify this is by thinking of how dense an object is. But here I'm thinking about the mean density. So this is, remember I mentioned there's a density, there's a change in density. So what about, let's think about not how density is in the centre compared to the outside. Let's look at the mean density of the sun. Most people seem to put yellow, which is what, I guess if you've done ASP3012, you would probably have seen this. So the Earth, in fact, has a higher mean density. And that's because those outer layers, even though the central regions of our sun are much more dense than the Earth, but because the sun is so centrally concentrated in terms of its mass, there is regions in the sun. And remember that density takes into account the volume. It's mass divided by volume. So because the sun has a lot of volume, there's not much mass out there, we tend to have the average density is actually quite low, and we'll do that calculation. So here's another question. The sun has an average density similar, so what sort of density does it have? Is it more like water, or is it more like air, or is it more like rock? So there actually are 4 choices here. Similar to air, and the Earth has an average density. So yeah, you have to read that one a bit more carefully. Now things do get cut off on the side there, so I will fix that for the next lecture. I see a mix of answers. So this is probably kind of mostly greens. Okay. Well, the greens win. It is similar to water, and the Earth has an average density similar to rock. And we can do that calculation. It's a very simple one. Again, assuming that the sun is a sphere and the Earth is a sphere, we can calculate the density, mass divided by volume, just again doing order of magnitudes. Sticking in the solar mass and the solar radius, we get a mean density of about 1.4 grams per cubic centimetre. Notice I'm doing grams per cubic centimetre. And this is approximately the density of water, but it's a bit more. The mean density of the Earth in comparison is about 5.5 grams per cubic centimetre, which is approximately the density of rock. And again, that's no surprise, where most of the mass of the Earth are composed of rocky material, which is, again, something, yeah, it's not so surprising. Okay, a couple of, we can also look at the amount of energy that the sun emits. I've put it there in a couple of different units. Again, I think in ergs per second, which is the CGS unit, and it's a weird unit. I will define it afterwards. But this is roughly 4 times 10 to the 33 ergs per second. If we want to put it in watts, it's 3.86 times 10 to the 26 watts. So this is how much energy the sun emits. And this is a harder question. And this is something that this is really something that we can calculate this, but this is really, unless you've seen this, I'll just leave you to guess this one. How much energy falls on the sun? So how much energy from the sun falls on the Earth per area per time? There actually are, and I guess I'm not going to say anything about this. I'll leave this as the last thing we do in this lecture. If you don't know the answer, take a guess. And you could Google the answer, but I'm not going to. But it will give it to you in. It depends on the units it gives it to you in. This is also a unit dependent. If you look at the units, it's a unit dependent answer as well. So I see a mix of two. I actually see roughly 50% pinks and 50% yellows, and that's because you're both correct. This is a trick question, and that both of those are the correct answers, just in different units. Okay. I think we can leave it there for today. I'm going to talk more about the sun. I'll finish up the discussion about the sun in the next lecture, and then we'll also then move on to timescales.